Welcome to the lecture video for section 3.3 in the textbook, and this is where we start learning about infinite series. So you'll notice at a few points in this video, I need to make a distinction between infinite sequences, lists of numbers that we've already learned about in the last lecture video, and infinite series, which are related but different. You'll see some similarities, but I really want you to treat these as different concepts that have similar techniques at certain junctures. I'll remind you of this right away when we do our first example as well. So the goals in this video are to first define what it means to have an infinite series and to identify the partial sums of the series. This is a sequence related to the series that we will use to evaluate whether a series converges or diverges. We'll also learn to recognize a few different types of infinite series. One is known as the harmonic series. Another, a related series, is the alternating harmonic series. We'll also learn about geometric series early on. And finally, we're going to learn a number of tests that will help us determine whether an infinite series converges or diverges. These include the divergence test, the geometric series test, and the ratio test. And finally, at the end of the video, we'll put everything together into something of a grand strategy for tackling series problems. So let's get right into it and talk about series that you've already encountered in your life. So you may have already seen sequences, just a list of numbers, what number comes next. These are all over social media. You've actually already seen infinite series too, although they were in disguise. So here's a couple examples. Any decimal expansion can be thought of as an infinite series. For example, 0.3 repeating, that's the decimal expansion that we know for 1/3, that fraction. You can even expand pi. We don't know all the decimal numbers for pi, but 3.1415926. Maybe a few more. You can go look these up. There are professional well, maybe not professional. There are competitions on Pi Day in March every year for how many decimal points you have memorized, if you're into that sort of thing. But in any case, we can at least expand each of these decimal numbers as a sum of a sequence of terms. And this is what we'll define to be an infinite series on the next slide. But for now, just intuitively, if we want to write out 0.33333 repeating, we can think of this as first add up the tens place, or the tenths place, 3/10, plus 3/100ths, plus 3/1000ths, plus 3/10,000ths, and so on and so forth. And the fact that these are different fractions with the denominator a different power of 10 means that they won't collide and cause any, carry the factor terms, anything like that. So these are really independent fractions we can add up separately. They have a clear pattern in this case, and we will learn how to show that this infinite sum of numbers adds up to 1/3, or this decimal expansion. On the other hand, something like pi, we don't really know a pattern for the decimal values of pi, but we can still think of it as an infinite series where we first add 3, and then 1/10, and then 4/100ths, and 1/1000th, and 5/10,000ths, and so on and so forth. You can keep going after that. This doesn't have a pattern. The denominators certainly have patterns, they're powers of 10. The numerator is this non-repeating, hard to understand sequence that that just goes on forever. We do know that there are infinitely many decimals after the decimal in pi. So you might have an intuitive sense what these quantities mean, what it means to write out a decimal expansion for different kinds of numbers. But the real crux of the issue here, if we want to write it as an infinite sum of fractions with powers of 10 in the denominator, you can call this the true decimal expansion of a number like this, is what does it mean to add up these infinitely many numbers on the right side of the equal sign? And this is where infinite series come in. We can actually do things in much more generality than just denominators having powers of 10. So let's take an infinite sequence from last time, a sub k, and we will form what's called an infinite series. In words, the summation from k equals 1 to infinity of that sequence a sub k will be the result of adding up those terms in the sequence in order off to infinity, a1 plus a2 plus a3 off to infinity. Now, this is just notation. It doesn't necessarily make sense to add up infinitely many numbers. For example, if you add up 1 plus 2 plus 3 plus 4 plus 5 forever, that won't have any actual value to it. And you can say, we'll eventually say that that infinite series diverges off to infinity. However, in certain circumstances, such as the previous example, the series, and this is just notation for now, can actually be given a value such as 0.3 repeating or 1/3. We'll prove this as our first example in this video. And sometimes the series may be converge to some number, but it's hard to say what that number is. For example, something like the harmonic series that I mentioned in the intro is the sum of reciprocals of whole numbers. This is the series 1 plus 1/2 plus 1/3 plus 1/4, etc. By the way, it's called the harmonic series because it shows up in harmonics in a physics class. We won't talk about why this is used in harmonics, but it's actually related to that other instance of the word harmonics in science. The harmonic series, I didn't write this series equals anything. We don't know right now what value to assign to it, if anything, but later we'll learn to determine if this can even be given a value, like the series above can be given a value 1/3. So this tells us what a series is. It's an infinite sequence. It's a sum of the terms in an infinite sequence, but it doesn't tell us how to evaluate it or how to assign a number like 1/3 to a series like this. So for example, how do we know that that series is 1/3? How do we know that if we add up infinitely many terms of the form 3 over a power of 10, that we get 1/3? So the true definition of a series is in the form of its sequence of partial sums. And this is where things get a little bit confusing with the difference between sequences and series. So I want you to just continuously remind yourself of the three notions that are going on here. First, we're going to start with an infinite sequence AK. I'll sometimes call this either the terms of the series or the coefficients of the series, but that's its own sequence, a list of numbers. Then we're going to add them up off to infinity, and that's the infinite series that we're using this notation for. So you can think of this as adding A1 plus A2 plus A3 plus A4, etc. And from that infinite series, we can extract what are called the partial sums of the series, and this is its own sequence. The first term in the sequence of partial sums, S1, will just be take the first term, A1. But the next term starts to differ from AK sequence. So S2 will just be take A1 and A2 and add them together. S3 will be A1 plus A2 plus A3, so on and so forth. So the nth term in the partial sum sequence is adding up A1, A2 up to AN. And here's the main definition in this video. We will say an infinite series, the sum from k equals 1 to infinity of AK, converges if the sequence Sn converges. And even better, we'll say that the series converges to L, and we'll even start writing the series equals L if the limit of that sequence Sn equals L. If no such limit exists, we'll say that the series diverges. And this, again, is exactly the same terminology as we use the sequences. However, there's a difference in this case between a sequence, a list of numbers, and a series, which is adding up those numbers off to infinity. Throughout the video, I encourage you, while you're taking notes on the side, to draw some arrows and point to the coefficient sequence or the terms of the series, that's AK in this slide, the series itself, which always has this infinite summation notation, and then the sequence of partial sums, which is a different sequence than the A sub k sequence. So every single series problem secretly has three ingredients: the coefficients, the series itself, and the partial sum sequence. Let's dive right in and do an example. Let's prove that this notation, this infinite series we wrote down, in fact converges, and even converges to 1/3 like we think it does. So I think doing this whole problem together would be a good idea. But one thing you can do is pause the video and at least write down the first three terms of this series, which are the first three partial sums, which are the first one, first two, and first three sums of the coefficient sequence, 3 over 10 to the k. So again, let me identify the coefficient sequence is just the list of terms in the series. That's 3 over 10, 3 over 100, 3 over 1,000. We can think of these as the individual decimal places in the sequence. And the entire series is what we get by adding all of them up. But what we need to focus on are the partial sums, which are the just finitely many terms added up. S1 is always just take the first term in the sequence. That's 3/10, or just to remind you, this is only the first decimal place in our decimal expansion, 0.3. S2 is not just the second term, the 100th place, but it's the sum of the first and second terms, 3/10 plus 3/100. And if we get a common denominator, this will give us 33 over 100. And that's not too surprising because that's exactly the first two decimal places in our full decimal expansion for 1/3. Likewise, S3 is, well, we can copy paste those first two terms that we wrote down. And then let's add on the third term, which is 3/1000. If I get a common denominator, well, think about it. It should be the first three decimal places. And a way to write that as a fraction is 333/1000. But you can check by getting a common denominator that we got the right thing here. Okay, well, we know that the nth partial sum intuitively is going to be take the first n places after the decimal. So we'll stop after we have n of these. We can even write this as 3, 3, 3. We'll have n threes in the top over, well, 10 to the n. I know how to write that. But I don't really know a good way of writing the numerator as a function of n or having an n in there. So I don't know how to take the limit of this sequence. This is why I left a double question mark here. We need to figure out a formula for the nth partial sum. And in part B, once we find that formula, we'll be able to compute the limit of that sequence of partial sums to evaluate this series. And we hope it converges to 1/3. And it's not immediately clear how to find a formula for Sn. But one thing that we can do is write down the difference between the terms of our partial sums and what we think the target is, what we think Sn converges to. So let's do this for each of the terms we've written down and see if we can come up with a pattern. So if you can go backwards in the video or take a look at your notes if you wrote these down. I'm just going to take 1/3 and subtract away S1. Well, now this is like taking 0.3 repeating and removing that first 3 in the decimal expansion. But how do we write this as a fraction? This is going to be, if I get common denominators, 10 minus 9, or 1/30. Okay, that's a pretty nice fraction. Let's see if we can spot a pattern in the next couple terms. So for S2, if we subtract it away from 1/3, that'll be 33/100 here. If we get a common denominator, I'll get 100 minus 99. That's going to leave us with a 1 in the top again, and 300 in the denominator. Let's do one more to check. Maybe you see the pattern, maybe not. Take a guess if you do. If I subtract 333/1000, I'll have 1,000 minus 999. Oh, that's a 1 again. That looks pretty good. Over 3,000. Let's try to together write down the general formula for not Sn directly, but for right now, 1/3 minus Sn. You can think of this as the amount that the distance between our partial sum and the actual value of the series that we're after. So 1/3 minus Sn, it looks like is a 1 in the numerator, just looking at this column of values. There's always a 3 times some power of 10 in the denominator. And what power of 10 is it? Well, it's just 10 to the n if we're using the nth partial sum. Let's just double check. For n equals 1, we got 1/3 times 10 to the 1. Yeah, that was 1/30th. And then we're just adding a power of 10 every time. So this looks pretty good. Well, this is nifty because we can now solve for Sn by, well, I mean, this is a formula involving Sn. So let's just solve for Sn and we'll get a formula for the nth partial sum of the series. Finally, we'll be able to take a limit of that to evaluate the infinite series. And we'll see that it converges to 1/3. But let's do our due diligence here. So Sn here, if I subtract, I'll have 1/3 minus 1/3 times 10 to the n. And I don't need to get a common denominator here because I'm going to take a limit in a moment. We'll see that the last term here goes to 0. So let's do it. As n goes to infinity, I have the nth partial sum in the series is 1/3 minus 1/3 times that power of 10. And as n goes to infinity, that second fraction goes to 0. So sure enough, we're left with a value of 1/3, just like we wanted. Okay, good work. So now we know that the series the sum from 1 to infinity, 3/10 to the k, converges to the value 1/3. That's what we just learned. We will do some more examples where we show convergence or divergence, but this is a particularly nice type of series that we'll want to learn a little more about in a moment. By the way, if you go to the interactive version of these slides, you'll be able to see this slider that shows how the values of the partial sums get closer and closer to 1/3. So it's hard to see on this slide what exactly is going on, but I encourage you to go and play around with the sliders here. The main idea of the previous example, and this will work for some types of series, is if we have a target in mind for the value of the infinite series, it may be advantageous to compare the partial sums to that target L, and showing that that converges to 0 would be enough to prove that the series converges to L. But at least if we can come up with a formula for L minus Sn, then we can get our solution started. So let's talk about the harmonic series. This was the second example a few slides ago. This was the sum of reciprocals of whole numbers. So 1/1 plus 1/2 plus 1/3 plus 1/4 off to infinity. If we look at the sequence of partial sums, you'll notice something funny happens. So the first partial sum is 1, and then we have 1 plus 1/2, that's 3 halves, and then 1 plus 1/2 plus 1/3, and then you have to start getting common denominators. But what's nice is if we look at the partial sums that are of length a power of 2, for example, here's S8, 1 plus 1/2 all the way up to 1/8. We can actually group together the terms in an interesting way. If we first replace all of the terms that are not a power of 2, like 1/3, 1/5, 1/6, and 1/7, with the next closest 1 over a power of 2 that it's related to, let's bump 1/3 down to 1/4. That makes the expression smaller, so we'll see there's an inequality. We'll move 1/5, 6, and 7 all down to 1/8. That makes the entire expression smaller. We can group together terms now. So the first term is still 1, then we have a 1/2. And then the next two together are 2 copies of 1/4, that gives another 1/2. And then we have 4 copies of 1/8, that's another 1/2. We'll see that S8 actually is 1 plus a bunch of 1/2s. And you can use this trick to show that for any partial sum of the form S sub n, where n is a power of 2, let's say 2 to the m, we can actually show that Sn is larger than 1 over 1/2 m. And because m is the number of 2's in our powers of 2, that's the partial sum we're looking at, as m grows to infinity, we can just take this value to be larger than anything we want. So this tells us that the harmonic series diverges. This was a little bit of a fluffy proof, but if you look carefully at the way that sequences diverge, for any large number we choose, we have to be able to take terms of the sequence past a certain cutoff that exceed that value. In this case, what we're saying is for any c that we pick, for any large number c, take it to be 1,000,000 if you like, we can find some m so that 1 plus m times 1/2, 1 plus that many 1/2s is larger than c. And the same trick that we used for S8 will show that S sub 2 to the m, for that m value, will be larger than this 1 plus that many 1/2s. And that's, of course, larger than c, and therefore the terms of our partial sums will exceed that threshold c. The takeaway from this slide should be that the harmonic series, even though the terms are getting smaller, 1/2, 1/3, 1/4, etc., diverges still. So adding up infinitely many reciprocals of whole numbers still doesn't converge to a finite value. So what's going on here? Well, let's take a step back and think about what was going on with the 1/3 example, the 0.333 repeating. And in some sense, pi is similar to this, but it's harder to write down. So a geometric series is an infinite series of the form, the sum from 1 to infinity of a r to the k minus 1, where a and r are some numbers. A is sometimes called the initial term, and this is a good terminology. We'll see how to compute these quickly in a moment. And the R stands for ratio. It's called the common ratio between terms. The way to actually think about R is it's the value that we're multiplying in to get the next term of the coefficient sequence. For example, the infinite series, I'm going to start on the right side with the terms of the series. 1 plus 1/2 plus 1/4 plus 1/8. This is the infinite sum of reciprocals of powers of 2. This can be written as a geometric series with the starting or initial term a equals 1. You'll see that there's only a 1 here. And the common ratio r is what I have to multiply to get from 1 to 1/2 to 1/4 to 1/8. You'll see that I'm just multiplying an additional 1/2 in each term of the sequence. In the infinite series, it comes out as a sum of powers of 1/2. One thing that I didn't mention on an earlier slide, but it's written for you in the definition, is that I can start my series at different places. So when we're working these problems out, sometimes geometric series, we can start at k equals 0, so that this coefficient, or sorry, this exponent up here is just k. We will have a formula that works in either case, but intuitively, you can start these series at different places and still add up to a finite number or still diverge. Our sequence that our series that we already wrote down that converged to 1/3, the infinitely many terms look like 3/10, 3/100, 3/1000. The way to think of it is we start with the initial term, a equals 3/10. That's the first thing in the lineup. And then to get to the subsequent terms, we just have to multiply by an additional power of 10 in the denominator. So in this case, we see the geometric series is of the form 3/10, that's a, times r, which is 1/10, raised to the powers of k. Let's try to maybe bite off more than we can chew, but evaluate the series a r to the k minus 1 for any a and any r. We already did this for a equals 3/10 and r equals 1/10. That was adding up to 1/3. Let's see if we can find the limit of the partial sum sequence in this case. This is going to take a little bit of work, but we can use some of the tricks that we used on our 1/3 example. So to start, I wrote out a few things that I'll just gesture at to speed things up a bit. So let's write down what the nth partial sum of this series looks like. The nth partial sum, again, is start at the first term of the sequence, but stop after only n terms. And this written out term by term looks like a plus ar squared all the way up to ar to the n minus 1. Sometimes it's better to use this summation notation. It's a little more compact. But in this case, I think it's easier to write out the terms and see what's going on with what we're about to do. The nice thing about a geometric series is the only difference between adjacent terms is an additional power of r. So here's a nice trick we can use. It's sort of what we did in the previous example with 1/3, but it was maybe a little disguised in that case. So here what we're going to do is multiply the entire partial sum through by r and see what happens. Well, if I multiply every term by an additional r, we'll get ar plus ar squared all the way up to ar to the n. And if you compare these two expressions here and here, you'll notice that most of the terms they have in common. So why don't we do the thing we might think to do and subtract to get rid of some of the terms. If I subtract Sn minus r times Sn, well, AR and AR will cancel out. There's an AR squared next there, and those will cancel out. There's an AR to the n minus 1 in the bottom expression that'll cancel out up top. So I'm left with A, the first term in Sn, and AR to the n, the last term in Rsn. And because I'm subtracting, I'll get the expression A minus AR to the n. This is an amazing trick because this is, again, an expression in terms of Sn, just like we noticed something similar with our Sn for the 1/3 infinite series. And we can solve for that symbol S sub n. And if you do it carefully, you'll get the following formula for the partial sums of this geometric series A r to the k minus 1. They look like A times 1 minus r to the n, all divided by 1 minus r. So what we're going to do now is take the limit of this expression. You can think of this as the same thing. I mean, it's not just think of this. This is the same thing as starting at 1 and adding up to n of a r to the k minus 1. So this is a new fact we just learned. And if I want to really replace the n with an infinity and see what happens to the sequence, that's what we're going to do next by taking the limit of this formula. It's a really compact formula. Well, if we have an r raised to the n and we're taking n to go to infinity, we should be worried that that goes off to infinity as well. For example, if r was 5, 5 raised to the n is going to go to infinity. However, you'll notice that And r can be positive or negative. R could even be 0, in which case we would already be done with this problem. But if r stays between -1 and 1, not including those endpoints, you'll see that you can think of it as a fraction. And then r raised to the n will converge to 0, in which case our limit will look like a times 1 minus 0. That r to the n term will go to 0 over 1 minus r. If I simplify, I'll get a over 1 minus r. I encourage you to pause the video right now and see what happens if you plug in a and r for our 1/3 infinite series. See what this expression equals. Okay, so if r is between -1 and 1, then the series converges to a over 1 minus r. I'd imagine many of you will have this memorized pretty soon because it's a really nifty formula. I'll show it on the next slide as a theorem. Next, if r is outside of that interval, if it's bigger than 1 or less than -1, then the term r to the n diverges to infinity, or I guess I should say plus or minus infinity, depending on if r is positive or negative. And in fact, if r is negative and less than -1, I'm just going to replace this and say this diverges. It either goes to infinity or it oscillates. So either way, the sequence diverges, in which case the sequence of partial sums diverges, and the series is equal to the limit of the sequence of partial sums. So the series also diverges. So what happens if r is plus or minus 1? Of course, we can't plug r equals 1 into a formula like this for the partial sums. So I encourage you to go back to the start of the problem and plug in r equals 1 and r equals -1 and just see what happens to the infinite series. I'm not going to do this for you, but I left a little space so you can do this in your notebook and work out what happens in those cases. If you don't feel like working this out yourself, let me show you now the theorem that governs all possible geometric series. This is a big theorem. I'd imagine that most people will have this memorized soon. Before I do that, actually, because we just worked out 3 different cases where r is less than 1 in absolute value, equal to 1, or greater than 1, these are what the sequence of partial sums actually look like for 3 different values of r. The light blue ones where r is less than 1, this is the sequence of partial sums, but it looks like these are sort of tapering out and we might actually converge to something. For the other 2, the gold and dark blue ones where r is 1 or greater than 1, it appears that those are not converging to anything, they're just going off to infinity. And indeed, the theorem is as follows. This is called the geometric series test. If we have a geometric series of the form the sum from 1 to infinity of a r to the k minus 1, then there's a formula for the nth partial sum, which is given here. If r is not equal to 1, we already worked this out. If r equals 1 and you did the exercise I told you to already, you'll just get the following expression for the nth partial sum. And the series converges when r is strictly between -1 and 1 to that formula we already determined, a over 1 minus r. For every other value of r, including plus and minus 1, the series diverges. This completely characterizes the behavior of geometric series, and we will see as we finish the rest of the video that this is the best case scenario for infinite series. To know everything there is to know about a series is usually pretty difficult. Here's some geometric series to practice with. So I just gave you a theorem that tells you how to evaluate the behavior of geometric series, and these are all geometric. So let's think about each of these together. So first of all, if I have the infinite series just written out term-wise, 2/3 plus 4/15 plus 8/75, I want to identify a pattern and write this as an infinite series notation with a coefficient sequence inside. So the numerator looks like powers of 2. I'm going to write 2 to the k and just double check my guess. If I plug in k equals 1, do I start at 2? Yeah, that looks good. 2, 4, 8, etc. In the bottom, I notice I have 3 times, looks like powers of 5. So I always have 3 times something. And if we think it's geometric, what do I have to multiply it by to get to the next term in the sequence? Well, it looks like some power of 5. And I just want to start at the right place. The first term just has 3 times nothing, or 3 times 5 to the 0. So I'll start at 5 to the 0, and that's where k minus 1 equals 0. If you weren't able to do this on your own, you can play around with writing out different powers of 5 and see where you need to start that sequence of 5s. And if I start with the index k equals 1, I'll have to use the pattern 5 to the k minus 1. Another way to do this, by the way, is if we put a 5 in the numerator, but that seems maybe a little superfluous to me. Let's just put all the powers of 5 together in the bottom. In any case, let's practice writing out our initial term a. And here it's always going to be the first term of the sequence of coefficients. But another way to do this is plug in, and this will always work for geometric series, plug in the first k value in the series. Here it's k equals 1, and just read off the first expression. For k equals 1, we get 2 in the numerator over 3 times 5 to the 0 is 1. So 2/3 is a. But again, we see it here. And then next, r is what I have to multiply by to get to the subsequent terms. I have to multiply by an additional 2 in the numerator and an additional 5 in the denominator. If I had written this carefully as a sum, I'm going to drop the indices of, well, now maybe I need to write it as 2/3 times 2/5 to the k minus 1. This is really the form a r to the k minus 1. Then you'll see what r is. But I think a better way to do it is think about it as initial term, and what do I need to multiply by to get to the next term? So the question in the geometric series test that we need to answer first is r between -1 and 1? In this case, it's 2/5. So yes, that's less than 1 in absolute value. And that means that the series converges, and we have a formula for what it converges to. So let me show you a and r again. A geometric series that converges always converges to the number a over 1 minus r. Here a is 2/3. R is 2/5. So we just need to do a little bit of arithmetic. Of 2/3, the bottom is going to be 3/5. And if I flip this fraction over, 2/3 times 5/3, wait, did I do that right? Yeah, 5/3. That's going to be 10 over 9. So this infinite geometric series, 2/3 plus 4/15, etc., converges to the value 10/9. I didn't show the other parts of this problem. I want you to do those as exercises. Let me show you the other series to add up. I can say a word about each of these before you write it out yourself, though. So if you look at the terms of the infinite series where we're adding up powers of 3, to get to the subsequent terms, we need to multiply by an additional 3. So here r equals 3. And if r equals 3, that's greater than 1. So we expect part B to diverge. I want you to write this out carefully, though. And then as a challenge, we added up the sequence that gives us 1/3 as a geometric series. That was our first example. And I want you to also express 0.9 repeating as an infinite series. It'll be the sum of 9 over powers of 10. And see if that converges or diverges. This might have been a controversial issue in previous math courses. Is 0.999 repeating equal to a certain number? I bet you have a guess for this. And using a geometric series, you can show that this does converge to that number. I'm not even going to say it because I know it's a big controversy, but it's true. This 0.9 repeating equals the number you think it does. Okay, well, going in a different direction, many series are not a geometric series. They don't have that form. For example, the harmonic series 1 over k was an example. But there's a nice test called the divergence test that tells us if series have to diverge. And here's how it goes. Usually it's written backwards from this, and in the classwork, you'll see a different version of this test. But the way we'll use it in practice is as follows. If we have an infinite series, the sum from 1 to infinity of ak, that coefficient sequence ak, if that coefficient sequence ak does not converge to 0, if its limit is not equal to 0, then the entire series has to diverge. In plain English, if the terms of a series do not converge to 0, which is a pretty strong condition, then the entire infinite series cannot add up to a finite number. A very strong caution for this theorem is this remark, which is if the limit of the coefficient sequence is 0, the test is inconclusive. Or in other words, we don't know if the series still converges to some finite number. The classic counterexample to this is our harmonic series, which you can go earlier in the video and take a look at again. We showed that it diverged, but the terms of the harmonic series 1 over k, remember it's just reciprocals of whole numbers, converge to 0. The limit as k goes to infinity of 1 over k is 0. However, the series diverges. This is not a contradiction to the theorem because you have to read the theorem in the correct order. It only says that if the terms don't go to 0, then the series has to diverge. It doesn't tell us anything if the terms do go to 0. And this is important. What does the divergence tell us, the divergence test tell us about each of the following series? So this is a good exercise to do on your own. I'll say a few words in a moment about each of these, but pause the video and write each of these series down, or at least write the coefficient sequences, and see if you can work out the limits of AK, just the coefficient sequence by themselves. If you get something other than 0, the divergence test tells us that the series diverges. If you get something equals 0, the divergence test doesn't tell us anything. So I want you to carefully work through each of these on your own. I'm going to switch over to the tablet and write a couple things on this example, but I won't write out every step. We'll do some of these in class. So here's the 4 parts of this problem. What does the divergence test tell us about the infinite sum of powers of 3? Well, the limit as k goes to infinity of powers of 3 diverges. I'll even write this goes to plus infinity, but that's not equal to 0. So A, that infinite series has to diverge. I asked you to do this one a moment ago as a geometric series. This is confirmation that that geometric series diverged. The terms of the sequence are getting bigger, but in particular, they're not converging to 0. So the divergence test tells us what happens. Here's our harmonic series again. So the limit here of 1 over k, I'm going to start being sloppy with my notation, but you should not do this. The limit here is 0. But that means the test is inconclusive. Again, strong caution. If you get a limit of 0, you don't know anything. If you get anything else for your sequence limit, then you do know the series diverges. What happens for parts C and D? I want you to work these out carefully on your own, but I'll tell you that I can look pretty closely at C and see that the terms of the sequence are not going to converge to 0. So this will diverge. However, in part D, I can see that e to the k will win the race, and this will be an inconclusive test. Notice that when we use the divergence test, the only possible conclusions are either, I wrote diverge or inconclusive. Those are the only possible conclusions from this test. I really want to drill this home. Okay. We're going to learn one more test called the ratio test that actually tells us when things converge or diverge. This one's pretty powerful. And rather than trying to work through all of the reasoning behind it like we did with the geometric series test, I'm just going to state the test as follows. So the ratio test says if we have an infinite series of the form, the sum of terms a sub k, and we compute the following value, we'll call it capital L when we apply the ratio test. It's going to be the limit of the absolute value of the ratio between subsequent terms, or mathematically, the limit as k approaches infinity of the absolute value of a sub k plus 1 divided by a sub k. If we call that limit L, if L exists and is less than 1, then the ratio test says the infinite series converges, and it does something better. It converges absolutely. We're not going to talk too much about this, but it converges. That's the punchline. If that limit L, the limit of the ratios of terms, converges to something greater than 1 or diverges, then the infinite series also diverges. Unfortunately, there's a spot where the ratio test fails or is inconclusive, just like the divergence test, which is where that limit capital L equals 1. So if the limit of the ratios of adjacent terms is equal to 1, the ratio test is inconclusive. We're out of luck. We've actually already seen examples of geometric series where the ratio test will give you an inconclusive result, but the geometric series will tell you that the sequence, or rather the series, diverges. I won't reveal exactly which those are, but you can go back and look at subsequent terms for ratio tests and see how for geometric series and see how the ratio test behaves. Just as a small remark on this notion of converging absolutely, we're not going to delve too much into detail about this for now, but if we have alternating positive and negative terms, we'll call that an alternating series. Converging absolutely means that if we took out the negative signs, or if we took the absolute value of all of the terms of our series, then the series would still converge. This is a very strong form of convergence, which implies that the original series also converges. Alternatively, we could only have something called conditional convergence. This is a weaker form of convergence, which involves both the positive and negative terms, not taking any absolute values. And if that series converges, but its absolute value counterpart diverges, which is possible in practice, then we'll call this a conditionally convergent series. For example, there's a series called the alternating harmonic series, which is take our harmonic series, remember that was 1 over k for its terms, and put a plus or a minus sign on adjacent terms. So we'll let the even terms be negative. 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, etc. This is an alternating harmonic series. It turns out that this series converges, although we won't be able to prove this together. If we made all of the terms positive by taking absolute values, this would just be the harmonic series which diverges. So the alternating harmonic series is an example of a series which converges conditionally, but not absolutely. All geometric series either diverge or converge absolutely because of the conditions on R involved. And anything for which we use the ratio test will converge absolutely or diverge, or the ratio test won't tell anything in that case. So we're going to talk about this after doing another example, but the real issue with infinite series is there are so many different techniques that we need to know to handle different situations, and no particular technique is perfect. There's some overlap between them. For example, the ratio test and geometric series test overlap for geometric series and tell you similar information, but none of them perfectly solve every infinite series problem. So we really need a constellation of different tools, or even a toolbox of infinite series tests. We've learned some of them in this video. There are some more in the packet, and there are even more than that we won't learn this semester. So here's a problem with 3 parts applying the ratio test. I'm going to do part B with you, and you're going to do parts A and C as practice on your own. So together, let's work out part B of this problem using the ratio test to determine if the infinite series with terms 2 to the k over k squared converge or diverge. In order to work out what the ratio test says, we need to compute this limit, sometimes called capital L, of the ratios between subsequent terms. So I'm always going to start with this limit of absolute value of ak plus 1 divided by ak. And then we need to plug in what ak plus 1 and ak are. Sorry, that got a little sloppy. So notice for part B, all of the terms are positive, so I don't even need absolute values here. In general, it's a good idea to include them until you realize that you can drop them, or you can eliminate some things using absolute values. So here, my a sub k plus 1 term, I'm actually going to write this as a k plus 1 as a fraction here, and then I'm going to flip my fraction for ak and put it here. This is a trick that we often use to evaluate things a little quicker for these ratio tests. So for ak plus 1, I'm just going to plug k plus 1 in everywhere I see a k in the terms of the sequence. So 2 to the k plus 1 and then k plus 1 is now getting squared. So that's my k plus 1 expression. And then I'm just going to take this and put in k's everywhere, but flip the fraction over. So 2 to the k is now on the bottom, k squared is now on the top. And it's my job, it's your job, but we'll do it together for this one, to evaluate this limit if possible. The best strategy for a ratio test problem is to group like terms. So the next step, once I've written in the k and k plus first expressions, is to group all of the powers of 2 that I see in this example. I'll put those separately from the polynomial looking gadgets. And you know what I noticed? Both numerator and denominator for the polynomial stuff is getting squared. So why don't we just square the entire fraction? You don't have to do this, but I think we'll end up treating it this way, rather than foiling things out. So notice that the first expression, the powers of 2 actually cancel out. I have one more power of 2 on the top than on the bottom. So I just have a 2 here. And here I have, I have k over k plus 1. This is a limit of a ratio of polynomials. So we can divide out by the largest power of k. And I'll leave it squared, but we'll see that this converges. Okay, so the limit as k approaches infinity of this expression, this little bit down here goes to 0. So inside the parentheses, I have just a 1, which gives me 2. So now the question is, we've computed this limit. What does it mean for the original infinite series? By the ratio test, does this converge or diverge? It's a good idea to pause the video and think about it on your own to really drill in what the ratio test is saying. But if you aren't sure if you had to flip back, then let me tell you the answer. We got a limit of L equals 2, and that is greater than 1. And this means that the series diverges by the ratio test. So you want a small L value. You want a small ratio between subsequent terms in order to converge. You want terms to stay close to each other, in other words. Great. I want to point out one thing, which is that the ratio test does not tell you what the sequence, or rather what the series converges to. It only tells you if the series converges or diverges, or maybe it's inconclusive. So again, geometric series are so far the only ones we know how to add up by hand. A couple reminders you can read to yourself. These are just some tips on how to do the ratio test. And I provided a few more as we did that example. Finally, here's the last slide that I want to talk about together. We have a few different tests. We have the divergence test, we have the ratio test, and then the geometric series test is really specialized to that type of series. And this is a good way to approach any problem. If we start at the top, it's a good idea to first check, even just eyeball it, to get an intuition, if the terms of the series are going to 0 or not. By dominance just means potentially reduce the complexity to just see what's going on in the limit. And I'll explain this more in class when we do more examples of these things. But for example, if we have something of the form k over k plus 1, that more or less looks like it's going to 1 because you can just look at the dominant terms. There's a k in the numerator and denominator, just like we did in the previous example. So if these terms of the coefficient sequence go to 0, we have to move on. But if they don't go to 0, we're done. The series converges. That's the divergence test. Once we've dispensed with that, if they're not 0, here we are. If they're 0, or maybe it's hard to tell and you don't want to write out the limit, then the next step, unless it's a ratio test, unless it's a geometric series and you recognize it, is to compute the limit of the ratios using the ratio test. If this value is less than 1, the ratio test is conclusive, the series converges. If it equals 1, or it's hard to tell, then the test is inconclusive. And in that case, we'd have to develop some more techniques. We'll have 2 more techniques in the classwork activity. And if that's greater than 1, it diverges and we're done. So that's it. Parallel on all these areas, there's sort of 2 labels. These involve recognizing if it's geometric series. That's sort of a parallel track. If you recognize the geometric series, do the geometric series test. That tells you the complete answer. Otherwise, you have to use the other 2 tests. I'm not going to work this one out with you, but I want you to apply your strategy that you just learned to not the harmonic series, but maybe the square harmonic series. This is called a P series with P equals 2, which we'll learn all about in the classwork. But this is the sequence of reciprocals of squares. So the sequence of coefficients is 1, 1/4, 1/9, 1/16. But the series is 1 plus 1/4 plus 1/9 plus 1/16. And we want to decide if this adds up to a finite number or not. To summarize, I want you to think about the following questions on your own. What is the difference between a sequence and a series? And more specifically, what types of sequences are used to evaluate infinite series problems? Next, what is a geometric series and how do we evaluate one? What is the geometric series test if you can write it out on your own? What does it mean to say that a series test is inconclusive? We have examples of inconclusive tests. But what does it really mean when those tests don't tell you anything? Finally, for each of, or not finally, but almost finally, for each of the following types of expressions, how do the factors behave in the ratio test when we write out k to some constant, or a constant raised to the k, or k factorial? How do you evaluate these when they're in a ratio? And finally, how do you apply the ratio test to geometric series? That's just an extra confirmation that the geometric series test is valid, but the geometric series test is really the way to go with these. All right, that is it. I left you a few exercises along the way that I hope you'll do, but I will see you next time. Thanks for tuning in.